Hello viewers, welcome to Dr. Ambedkar Open University. So today we are in Teleconference. So Dr. Ambedkar Open University is the first open university in India and it is established in 1982. That university is offering the UG program and PG program and PhD program also. That the university is provided printed material and as well as the video lessons and audio lessons. So many facilities are in that Dr. Ambedkar Open University. So please utilize that. Today we are going to discuss the topic about in mathematics BSc 3rd year 6th semester. So the elective paper is there, DMS. So in the DMS, so we are going to discuss about the topic name is fundamental logics. Okay, so it is very important topic and it's very easy topic. So students, so first there is a 1 hour program this is. So first 40 hours, so we are discussing what are the topics are in that fundamental logical. So after the 40 minutes, so remaining 20 minutes, so we are interacting with phone in program is there. So if you are any doubts, so after complete the 40 minutes, after listening that all the PPT, so just you have to interact and after the 20 minutes, you are interactive with the experts here is there. So the phone numbers is 040-23680-456. So once again I will repeat it student 040-23680-456 there. So here today we have the two special experts in the mathematics. So one of the expert the madam is there, Dr. Vijayalakshmi madam, a professor, and here that one more expert is there, Dr. A. Nagaraju, professor, and that is MLIT Hyderabad. So, okay, yes. So these are the two experts are there and very there are almost 30 years service in that mathematics and in the teaching field and very expert person is there. So after listen the 40 minutes and you can ask the any doubts regarding this one. So we will start that program now. Okay madam, now you can start that what is the fundamental logic and what is the use of this topic in your personal life generally. Actually mathematics we cannot use any in personal life, that is addition, subtraction and division, multiplication is there, just we are using that calculator also. But what is the use of studying this fundamental logics and whatever may be, just give some sentence about that, how we can use this fundamental logic in general life. Now that madam will
mathematics some statements we can't prove directly. For example, if you take if you want to prove root 2 is an irrational number, we go by contradiction method. What is the reason behind by using these kind of different methods of proof? Some problems we are doing with direct methods, some we are applying some mathematical logic. So what is this logic? Logic is a discipline like other courses. This is a discipline that deals with the methods of reasoning. Mathematical logic is the study of formal logic. Within elementary level, logic provides rules and techniques for determining whether a given argument is valid or not. Logical reasoning is used in mathematics to prove theorems, and in computer science it is used to verify the correctness of programs. Dear viewers, today we are going to discuss what are these fundamentals of logic, like statements and basic concepts of basic connectives and truth tables, logical equivalences, the law of logic, logical implication and rules of inferences, use of quantifiers. If the time permits, we will go for different methods of proofs or proofs of theorems also. Begin with what is a statement? First of all, we start with a statement. Suppose if I say an elephant weighs more than a human being, what do you say? Yes, it is correct. Suppose if I say Hyderabad is the capital of Telangana state, yes, it is correct. If I say Hyderabad is the capital of India, so it is no. So like that, what are the first of all, observe these kind of sentences. Get up and do your homework. Why are you playing here? All this, observe some kind of sentences. So you have sentences are usually classified as declarative sentence, exclamatory sentence, interrogative type, imperative, etc. But Here we are not interested in all those statements. What is a statement? Statement is a sentence, or a sentence is called a statement if it is either true or false, but not both. A statement is a proposition, or you can say a proposition, statement, these are all having and this one same meaning. So, what is a statement? Statement is a proposition, or it is a declarative sentence which is either true or false. Suppose if I say Italy is a country, so it is a true. Mumbai is the capital of India, false statement. If I say 2 into 3 is 6, then it is wrong. So, in this way we will categorize statements, sir.
Sir, which kind of sentence are not statement? Which kind of sentence which are not statements?
Sir, here it is a some statements are may not be, it is a proposition. Why? Because of it is a proposition well there, then only we can apply for the logical equivalences and any implementations of execution of weather programs.
Yes.
Here statement cannot give that kind of the statements are the explanatory statement. Explanatory means it is a question, it is a doubtful, it is a yes, ho. Such kind of statements, it is there is no any meaningful, so that such kind of the statements we cannot take that is a declaration statement, so that it is not a proposition. That such kind of the statements, and not only that, it is some more statements are the we can take that is a explanatory statement. Explanatory statement, not only this, it is a interrogative statement. Interrogative statements, it's a why, when, where, such kind of the statements will be there. That's kind of the where he will, example is a where he will go to, where you will do.
Yes.
That kind of the statement is a something is a question mark.
Okay.
So there we cannot take the directly, it is a true or false.
Yes.
Either true or false, if anyone will be there, then it is a declarative statement. It is not there, so that we cannot take. Such kind of the statements are the here explanatory statement and interrogative statement and imperative statement. Imperative statement is it is a demanding statement. Okay. Demanding means, hey, you do. That is what is that? It is, there is no any statement, it is a clear statement. Demand is there. Yes. So clearance is not there. Here he can do it, he cannot do it. So such type of suspicious sentences are not the statements. These are the three ways we can take. It is a declarative statement, so then only we can apply the logical implementations. Logical implementations are there, then we can implement. It is for example, it is here Mumbai is the capital of India, maiden said. It is clearly, it is one of the clear statement. It is a declaration. So that such kind of the statement point of view, here multiple statements we have, then we can implement. Then we can judge, we can check that is whether logical implementations are exist or not.
Okay.
Here whether this is a explanatory and interrogative and imperative, such kind of the statements cases we cannot do it. That cases are we cannot judge, so that here the statement aspects, it is a logical implications we cannot implement.
Yes, sir. Nice explanation. Thank you, sir. Next, ma'am.
Precisely in which the sentences without truth values are not statements, and we can combine these statements with logical connectives. So connectives are used to create a proposition from several other propositions. So the most commonly used connectives are negation and or and exclusive or implication and biconditional or if and only if. So these are the connectives we are going to discuss today. Sir, yes.
Sir,
here connectives means it is a example is if I take that, it is a whenever that single statement cannot give that is a full information.
Okay.
So at the time we require that is a multiple statements, then we can get that is a full of information.
Okay.
Any artificial intelligence example, if I take one device will be there. That device is if we tell that is only one statement, there only it will be hold.
Yes.
Other statements will be there, then continuation what we will do, that we can get.
Yes.
It is the implementation point of view, both are the statements. Connectivities are there. The connectivities are called as here connectivities we have, that is and or jar and negation and implementation by implication. Such kind of the statements are called as the connectivity examples, connectivities. Here example, if I take that sky is clear, it is one of the statement. It is another is it is raining. So I am connecting that is these two statements. It is for example, it is sky is clear and it is raining.
Yes.
So it is a two connections, two sentence statements. I am going to connect it. Here I use that is a here and operation.
Yes.
That is called as a operations.
Operation.
That operations are we are using here and operation and OR operations, XOR operations, NOT operations, and such kind of all operations we can use it. Here, for example, NOT I want to use. NOT when we will be used, particularly here, I want to go to Delhi. This is one of the example. For example, if I may or may not be going, but
Yes.
it is a decision is I am going to Delhi because of I have a ticket.
Yes.
So it is a the flight is cancelled. So that what I can say it is I am not going to the Delhi. So
yes.
that not means I have to use that is a situational I have used. So that there I have to use the operator. That operator is a not operator. This is one of the application. Now I am going to discuss that one of the first is a truth tables. So what is the meaning of truth tables? Here two statements are there.
Okay.
Here madam in the initially mentioned that one of the here it is a statement, it is a proposition. Proposition means it is that statement is clearly true or false.
Okay.
True means it is we can take that is indication is take 1.
Okay.
Here false means indication takes the 0.
Okay.
Here 1 and 0 in between the binary operations can be conversion.
Okay.
So that it is a statement I want to convert into the binary numbers.
Okay.
The binary numbers if I want to convert here operational see how it will be the effective.
Okay.
That effectiveness we can confirm that by using that is a truth tables.
Yeah,
Here truth tables one relationship between the truth tables is indicated that here true here and operation I am using.
Okay.
And operation I am using here and in between means it is a true.
Okay.
Remaining all are the false.
Okay.
Remaining all are the false. At the time it is a and operation if I use.
Okay.
Next negation. Negation means it is clearly I will use that is a not. True. True means false.
Okay.
False means true. That is called as it is a negation. It is a and operation. It takes that is a true and true false and
Okay.
false true also false. False also false. This is kind of the relationship is exist and it means that true means it is a first statement is a true, second statement point of view it is also
False,
true,
true.
then only true, other cases are the false. That is called as a and operation. And the negation means it is a one statement I want to give into the negative way. That is a true is called as a false and false is
called
true.
true. Yes.
That is a negation. Next it is goes to the another is a another operation.
Sir.
OR operation.
Okay.
OR means it is a what it is going to the OR operation. OR operation is clearly mentioned that here any two statements here there we will use that is operator name is called as a gap.
Okay.
GAP gap.
Gap.
Here P is a one statement and Q is another statement.
Okay.
P gap Q.
Okay.
If I take that, what is the conclusion? Means it is a two statements. I am middle. I am using that OR.
Okay.
Either of that. Either I mean that it is a OR means it is a I can do this one or that one.
Yes.
Anyone will do it is a success we can
Success,
get.
yes.
So that it is a truth table takes that is a true false also true, false true also true,
Okay.
and false also false is a false.
Okay.
Both are the false, then only false.
Okay.
Then it is at least one is a true. Then we can say that it is a true. That statement is called as a or proposition.
Or proposition.
Or operator we are using. That is a gap P gap Q we called. Now here I am going to the XOR operation. XOR
Yes.
means it is clearly here true false.
Okay.
And false also false.
Okay.
True false is a true and false true is a true.
Yes.
Such a statement is called as here we can say that it is a XOR operation. XOR operation. Here XOR operation.
Yeah.
Here XOR operation. What is a in between that we can use where we will be use this kind of statement. For example, particularly it is a total. It is a artificial intelligence or any Google Drive. It is a wherever the sentences are there.
Okay.
That statements having there is some errors.
Okay.
Even though that is having the sentence having the errors, that errors also we should be convert into the some conversion of the sentence formation, whether we can get the execution or not.
Or not. Okay.
Such kind of the cases we can use a XOR operation. Such
Yes.
cases we can use a XOR operation.
Yes. Okay.
Such cases
So on
we can use a
the
XOR
summary, and statement means meet. If P and Q are any two statements, P and Q means P meet Q. P meet Q is true only when both the propositions P and Q have truth values. P is Q, Q is also true. And P or Q, that means P join Q. P join Q is true if one of them is true. Whereas this exclusive or exclusive or we write it as P join Q like that. How if one of them is true, then it is true value, otherwise it is false. That means if P and Q have same truth values, it is false.
Yeah.
If one is true, other one is false, means it is true.
Yeah,
So
madam.
Here one more here
Yes.
and operation we
Yeah.
can use in the application orientation.
Yes.
Digital electronics.
Digital electronics.
Digital electronics mostly we are using.
Yes.
And our operations all are using the control system.
Yes, sir.
Control systems there we are using. Here error predictions point of view is our operations we are using.
So there are only 3 operations will be
No,
there.
here one more here is
One more,
implication and by
implication.
implication.
Implication and
Middle.
by
coming
implication.
to next connective, implication.
Yes.
Sometimes see, if today is Sunday, then it is holiday. That means if you take P and Q or any two propositions, then how the proposition P implies Q, that means which is denoted by P implies arrow mark Q. Okay, so that is called the implication. What does it mean? If P, then Q, when it is true. See here, P implies Q is called an implication, and the truth table for P implies Q is, here we have to observe one statement. Suppose if Isaac Newton discovered America, then there are 4 days in a week. Will you accept under any circumstances 4 days will make a week? No. So that is the reason, if whoever discovers America, it does not change the number of days in a week. So that is the reason false implication is always false. So your P implies Q is true when both are true, and one is truth implication is always true. If Isaac Newton discovers America, then there are 7 days in a week, always true. Why? Because whoever discovers America, it does not matter, number of days in a week is 7 only. If Isaac Newton discover America, then there are 7 days in a week, it is a true statement. That means truth implication is always true. And again here one more, here logic is false implication false. If P is false, Q is false, then false implication false is always true. Why? For same example I am quoting. If Isaac Newton discovered America, then there are 4 days in a week. On the whole, you see, anyhow we know that Columbus discovered America. So if Isaac Newton discovered America, then there are 4 days in a week. That entire statement is true because he did not discover America. So the entire statement is true. So false implication false is always true. So implication means, after implication, one of the next connective is biconditional. Biconditional means P implies Q and Q implies P. P implies Q and Q implies P, or P happens if and only if Q. A triangle is equilateral if and only if all the sides are equal, or it is a square, or a quadrilateral is a square if all the sides are equal, like that, if and only, if biconditional. When this P if and only if Q is true, see here, if it is having same truth values, that means whenever P is true, Q is true, then P if and only if Q is true, and both P implies Q and Q implies P, P is false and Q is false, then P if and only if Q is true. So if both of them are having same truth values, see here, suppose you are taking two variables, the P and Q. So how many combinations? See, every statement is having one truth value, either true or false. For every statement you have two truth values. So suppose you have taken 3 statements, P, Q, R, then how many truth values you will get? You will get 2 cube. That means you will get 8 values you will get. So after learning this biconditional, where we are applying? After, see here.
Yes.
What do you mean by P implies Q or Q implies P? Why we are taking so many?
Yes.
P implies Q, Q implies P. Why one statement? We are representing several ways.
Okay.
So P,
sir, are there any ways to connect to the proportions?
yes.
Yes.
So P implies Q means P is sufficient for Q,
Okay.
or Q is necessary for P.
Okay.
These are the meanings of this conditional. Converse means Q implies P. That means if Q, then P.
Okay.
Opposite means for P implies Q, opposite is negation of P implies negation of Q. Contrapositive means negation of Q implies negation of P. Students, in exam you will be asked to write the statements. You have to write the implication, converse, opposite, contrapositive. Look into this example. Suppose you have P implies Q. Consider if the quadrilateral ABCD is a square, then the sides of quadrilateral ABCD are equal. Tell me whether it is true or not true. See, if P implies Q, suppose if I take converse, Q implies P. If the sides of quadrilateral ABCD are equal, then the quadrilateral ABCD is a square. We can't say, sometimes sides are equal, but it need not be a square. So here, opposite if you take, if the quadrilateral ABCD is not a square, then the sides of quadrilateral ABCD are not equal. That is also false. But contrapositive, you observe P implies Q and negation of Q implies negation of P. Whenever P implies Q has a truth value, true, then contrapositive, negation of Q implies negation of P. That means if the sides of quadrilateral ABCD are not equal, then it is not a square. Whenever ABCD becomes a square, its sides are equal. If sides are equal, it doesn't mean that it becomes a square. So always P implies Q is true means its contrapositive statement is also true. You have to observe what is the converse of the statement, what is the opposite of the statement, contrapositive of positive of the statement.
Now, here construction of the truth table, if I observe that here if I take that it is a construction of the truth table, and I am going to give that as one example. Here these are the all the logics we can implement into the implications and by implication in the robotics designs. Robotics, how it is working, that conditional implementations all we can do by using the implies and by implies, what made me explain. Here that in this our observations is goes to the here operationals. It is a combination of compound operations. If we have whatever the resultant of the truth table results, result what it is a true or false, whether it is a true, then it is a we can go for that is a continuation of the next level. That is comes to the observations we can check by mathematically here. That is here we do this as one step is here true. Here I am taking the one example P cap Q or
P
gap,
meet Q, P meet Q, join
gap negative negative Q. It means that it is a what is it? It is a P and Q means it is a truth table. First I am taking to TT2, TTT and TFF and FTTF and FFF. Only both are the true, then only it is true. Others also it is a anyone is a fail, then automatically it is a false. So it is a such statement. Next it is a combination if I use. It will go for the negation of P, negation of Q. Negation of the Q is what is the negation of the Q? Here true is goes to the false and false is goes to the true. So here the first row we are taking the true is a false and true is a false and false is a true and false is a true. So then we can go for that is a OR operation. In between OR operation, what is the OR operation? At least one is a true, then we can go for the true. So here we can apply that is a P and Q or negation Q. It is goes to the here T for true false is a true and false true is a true and false false is a false and false true is a true. This is a example for that. It is a construction of combinations of it is a operational statements.
Yes, sir. Sir, are there any laws or rules or logical equivalences?
Oh yes, sir. It is one more example I am taking here. This is a proportional
three variables.
Three variables case. Three variables case here starting madam mentioned that it is a 2 power 3. It is means 8 possibilities we have. Here first is a P, Q, R are the three statements cases. Three statement cases, whether it is a logical implications is a possible or not. Yes, it is possible because of 2 power 3 means it is a 8 possibilities we have. 8 it is a statement. For example, first statement is true, second statement is true, third statement is true. Then what happens? It is a P and Q. It is if I apply, then after that negation Q. If I apply, by implies if I apply, what is true? Then it is a total. It is a relationship so we can get. Here 2 power 8 possibilities are we can first justify PQR. PQ 3 statements. One is a true, false. It means that is any one is a false. It is out of 3. It is that is a 3 combinations we can get. Next after that again we can go for that is a 2 or the false out of these three statements.
Yes.
Then it is a here also 3 I will get. All are the false, one statement. All are the true, one statement. Total is 8 statements.
Okay.
8 statements, whether it is operations are applied. So it is a P and Q and negation R I am finding. Then P and Q R, negation R I am finding. After that I will go for the implication of the P. Then I got it the conclusion. That is one of the example.
Okay.
Now here here you are mentioned that it is a we have a that is a 3 cases of propositionals. It is a tautology. Tautology means all the statements, whichever the operations you will apply. It is a statements are many. All statements are many. It is a in that also I will use the operations, various operations. I mentioned that 5. 5 operations if I use, and with the 3 statements or 4 statements, it is a total conclusion of operation is all are the true. Then we can say that it is called as a tautology.
Okay.
Then again it is go for the counterposition. Here contradiction. Here contradiction I will go for that. It is a contradiction is a here always all this it is a same, it is a PQR proposition, PQR statements. These 3 statements. These 3 statements here proportional relationships already operations after apply. I will go for that is the output of the what is the resultant. All the resultants are the false. Then we can say that it is a contradiction. Here all are the true. I said that is a tautology. All are the false. It is called as a contradiction. Some of them are the true. Some of them are the false. It is called as a contingency. These are the terminologies we can be used. Here I am going to give that is a one example. Here we can check that is a here I applied that is a PQR the 3 statements and I have the applied that is some relationships. Then output is I am getting all are the true, so that it is called as a tautology. Second example, if I go for that here implication, sir, you are mentioned that is a equivalences. Here equivalences means it is a logical equivalences. Logical equivalences here I am using that is a tautology.
Okay.
Here logical equivalences I am going to use that is a by implication. If I use, I can get that is a some more. Here example I am taking here. Here for example it is a equivalences. Here first 2 statements. What are the resultant giving in the using the operations? I am taking that is the same operations, same statements, and another operations I am using. At the time both are the comparison, both are the answers I am justifying. Both answers are the justifying. If it is the same answers if I get, it's the first what relationship I am getting the resultant, and another statement, another relationship resultant, both are the same, then it is called as a equivalences. Equivalences. Here I am getting that is a example. Here here first it is a PQ. 2 statements I am taking. Here true, 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 false, false, true, false, false. Here P implies Q I am taking. What is a true, false? True, true is a resultant. It is a negation P I am taking. Here after that F, true, true. Then it is a negation P or Q. Then it is a true, false, true, true. Here P implies Q, got it, that is a TF, TT. Again negation P or Q also getting that is a TF, TT. So some operational relationships are the equal, that is called as a logical equivalences, and the statements are that we can be used that is a, it is a operational equivalences, then we called as a logical equivalences. Here another example. If we take that, it is a PRQ, PRQ and R. 3 operations, 3 statements I am using here, PRQ and R. Then it is another is a PRQ and PRR. What is that? It is I am going to apply that is a distributive law. I am going for the checking that is a 3 operationals and 3 statements. What is it? It will be what? It will be the resultant will give that is a operational equivalence is we can get it, or distributive law I am checking. Yes, it is a first, it is a PQR I am taking here. What is the 3 operations I mentioned, 3 statements I mentioned. So 2 power 3, whatever it is a 8 relationships I will get. What is that? It is a true, 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 and true, true, false, and false, true, false, and false, false, true, true, and true, false, 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 true, and false, true, false, and it is a false, false, false. What about 8 operational relations? Now I am going to apply that is a operations. What is it? PQ and R first I should check. Then after that P, R, Q and R. Then it is I am getting the resultants are T, 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 F, F, F. Then I am going for that is a distributive second right side RHS. It is a P, R, Q and Q, P, R, R. Then it is a that is a resultant is I am going for the AND operation in between. I am getting the T, 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 F, F, F. So here P and Q, here P, R, Q and R is equal to the P, R, Q and P, P or R. It is called as a here distributive law is clearly satisfied. Therefore, it is a logically equivalences. So, three statements it will give, that is a logically equivalences. Here logical equivalences, some of the rules will be satisfied and some of the laws will be satisfied.
Okay, sir.
That laws are called as a domination law. Domination law, what it will say that it is a statement I will take and it is a one true statement, true resultant already I know. True already resultant I know,
okay.
And false resultant I know. Then one statement, it is a connectivity with the true or false. Then it is a resultant is always a true or false only we get. That is called as a domination law. Domination law. Next, another is called as a identity law. What is identity law? It is any statement with the true or any statement with the or relation with the false. Then it is a resultant is a P, and it is the only statement we can get. That is called as identity law. It is a we will apply that is a true or false with the statement with the operational relation. Then we get the same resultant of the statement. Then we can call it as a identity law. Then idempotent law. Idempotent law means it is a P or Q is also the same. P and P also P. Both are the same. It is a P or P also P and a P or P also P. That is called as identity law. Then we can go for the negation of the negation P. It means it is a double negation. Also we can get that is the same resultant of the statement. This is called as a negational resultant. Then we can go for
equivalence, commutative.
Next it is a commutative law. Commutative law means P or Q. It is implies Q or P. That is called as a commutative law. And operation we can apply or R operation we can apply.
Anything.
In between any we can get that is it is a relationships will be the same. P or Q or Q or P. And P and Q and Q and P.
Okay.
Both are the equivalence. That is called as a commutative law. Next it is a associative law. Just now we proved in the truth table three statements. That is a P and Q are equal to P or Q or P. That is a associative law. Then it is a distributive law. Just now we proved that it is a P and Q or R. It is implies that is a P or Q and P or R. Then it is comes to the De Morgan's law. Negation of the P or Q equal to negation of the P and negation of the Q. This is mostly we will use the most of the cases of various proofs. Then again we go for the implies law. It is called the P implies Q. Implies it is clearly negation of the P or Q.
All these students you can verify by making use of truth tables also. So here what you have learnt is tautology. Tautology means irrespective of truth values it is true. So why to always apply only truth table? Suppose if there are two variables, it is easy to form a truth table to find whether a given set of statements is a tautology. That means valid arguments becomes a tautology. So it is easy if 2 or 3 variables are there. Suppose 4 also, with great difficulty by taking 16 truth values we are able to check whether the given statements are valid or not. That is also very not difficult but is a lengthy process. So logical equivalences will give you the simplest way of proving the validity of the given statements. For example, you see, show that here P meet Q implies negation Q is a tautology using logical equivalences. For example, tell me what is P meet Q implies Q. This is nothing but just now we verified that P implies Q is equivalent to negation of P join Q. Here in the place of P we take P meet Q. So that is negation of P meet Q join Q. So again logical equivalences by making use of De Morgan laws. What is negation of P meet Q? It is negation of P join negation of Q join Q. So you are applying here De Morgan's law. Again you simplify, you apply associative law because you know that A join B join C equal to A join B join C. You apply what is the negation of P join, negation of Q join Q. Negation of Q join Q is applying associative law and negation of Q join Q is true. So what is the negation of P join truth value T? It is T, truth value only, T only. So what does it mean? You have P meet Q implies Q is a tautology. So what can you say? You can say that P P meet Q implies Q is a tautology. So, these are the logical equivalences we have used. What are we applied? Implication, De Morgan laws, associative laws, cancellation laws. So, one more we will see. Next example you see, and whatever the sir explained about distributive property, that is also you can prove by making use of this equivalence formula. One more you see, negation of Q implies P, join P meet Q is logically equivalent to Q. Students, you can make use of truth tables also. You prepare a truth table, you will get the truth values of left side statement is the same as Q. But by making use of logical equivalences, we prove like this. See, negation of Q implies P, join P meet Q. Apply their implication law. What is the negation of Q implies P? It is a negation of Q join Q meet negation of P. There we are applying this one. See, negation of Q join P meet Q. Again you apply Q meet negation of P, join P meet Q. Here we are applying De Morgan's law and double negation. We know that negation of statement P is P only. So, again apply distributive property. What it is? Q meet negation of P, join Q meet P by applying commutative law. Then you apply distributive law. It is Q meet negation of Q join P. See, distributive law. Like that you have to mention each and every law, and it is very easy to prove the logical equivalences. Otherwise what you have to do? You have to prepare truth values for P and Q, form a table form truth table for Q implies P, then its negation, then P meet Q. All this you have to do. So, you see how much hard work is reduced. So, this is called smart work. By doing smart work, we can easily prove logical equivalences. Sometimes here also two statements are there. We are able to prove this. But if you are given more than compound statements, more than 4 or 5, then it is tedious. It is a very lengthy procedure to prove these equivalences. So, for that we are going to use inference calculus or inference theory. What do you mean by an inference? Okay, the word inference will be used to designate a set of premises. Premises means what are the arguments you have given. So, today is Sunday. If today is Sunday, it is a holiday. So, if it is a holiday, Ramu will not do homework. Again, if Ramu will not do homework, then his teacher will scold next day. Like that, if you are given so many arguments, you have to check finally. Ramu, he got very good marks. Suppose whether the following conclusion is true from the given premises. So, premises means what all the statements or arguments you have given. So, after that what we have to do? We will take the conjunction. First of all, what are the sentences or statements are given, we convert it into we convert them into what you call connectives, compound statements, and we will write them symbolically, and we will apply 4 major rules of inferences. Generally what we say, each inference can be written as an implication. What it is? Conjunction of premises is always implies conclusion. So, here we are going to talk about the rules of inference. Students, there are total 8 laws to solve or to check whether the given arguments are valid or not. Out of that, we have discussed mainly 4. What are they? What is the fundamental rule? Fundamental rule is rule of detachment. Rule of detachment or modus ponens. That means, suppose P is true. The statement P is true and P implies Q. Therefore, Q. Suppose if I say if today is Thursday, 3 days after will be Monday. So, today is Thursday. So, what is the so 3 days after is Monday only. Like that, this is in this way we can make use of rules of inference or modus ponens. What it is? P and P meet P implies Q. P meet P implies Q. Implies Q is a tautology. If you want, you can check with your truth tables. So, what is the example? If the triangle is isosceles, then the triangle has two equal sides. The triangle is isosceles. So, what will be the conclusion? Triangle is isosceles means the triangle is having two equal sides. Or if today is Thursday, 10 days from now will be Sunday. Today is Thursday. What is your conclusion? Hence 10 days from now will be Sunday. So, this is called modus ponens fundamental rule number 1, which is also known as rule of detachment. P meet P implies Q. You have to register these formulas in your brain. You register them. P meet P implies Q. Implies Q is a tautology. This is the modus ponens or rule of detachment. Next one, fundamental rule 2 is hypothetical syllogism or transitive rule. What is you mean by transitive rule? If 4 is a multiple of 2 and 8 is a multiple of 4, definitely 8 will be multiple of 2 only. In mathematics, by making using numbers also you can tell, or you have, if 1960 was a leap year, then 1964 was a leap year. If 1964 was a leap year, then 1968 was a leap year. So, what is your conclusion? If 1960 is a leap year, then 1968 was a leap year. So, the rule of hypothetical syllogism or transitive rule says that if P implies Q and Q implies R, P implies Q and Q implies R, then P implies R. That means P implies Q meet Q implies R implies P implies R is a tautology. Okay, not only for these two statements, you can apply hypothetical syllogism for more than 2 implications. That is, if P implies Q, Q implies R and R implies S, then P implies S. Like that you can. Next, De Morgan laws already we have discussed, and fundamental rule 4 is law of modus tollens or contrapositive. Already I told you, whenever P implies Q is true, then negation of Q implies negation of P is also true. That means P implies Q and then, or P implies Q if and only if negation of Q implies negation of P. That means this is called modus tollens. How you write? P implies Q, negation of Q, therefore negation of P. So, see here, if all of us know geometry, if lines AB and CD are parallel, then the alternate interior angles alpha and beta are equal. Suppose if alpha and beta, but the alternate interior angles are not equal. Given ABCD are parallel, if the lines ABCD are parallel, then alternate interior angles alpha and beta are equal.
Yes.
But alternate interior angles alpha beta are not equal. So, what do you say? The lines are not parallel.
Yes.
Because we know that two lines are parallel. Whenever two lines are parallel, then alternate interior angles are equal. Similarly, you can give in many examples, if it is not raining, the sun will come out. The sun will not come out. So, what do you mean? It is raining, like that. Okay. After this rule, let us see, using the rules of inference, build arguments. Sir, Nagaraju sir, explain this.
Building these arguments means it is clearly we are taking that any statements. That statements it is here what reason that acceptance is working. That is the conclusion part of we can be decide. That is called as a premises. Here negation of the P and Q. And comma another is a R tends to P, another is a negation R tends to S and S tends to T. These all are the assertions. If I take, what are the above fundamentals are applying, that is called as a here first statement is what he has given, negation of the P and Q. If I take, it is called as a hypothesis. Hypothesis is what he has given, that is I am taking here, that is the reason. Next is the negation P I am applying, it is called as a simplifying using of the statement hypothesis one. Then again next I am going for that, it is a R tends to P, it is called as the hypothesis already he has given, so that I am taking that is a hypothesis. Next, negation or. Negation or means it is a modus tendency using that is a 2 and 3. Directly we can conclude that it is a negation or tends to negation. S is called as already has given the hypothesis 3. So here S is a modus ponens using the 4 and 5 and S tends to T. That is a hypothesis already has given. So conclusion of that T is a we obtain. That is a statement of the modus ponens using. So it is called as a building the arguments. We called as a building the arguments. It is clearly inferences we are using. So rules of inferences and to the building the arguments. This is one of the
same thing we can do with the truth table also, but you have 4 statements are there. 4 statements, you have to take 2 power 4, 16 truth values, and you have to make their conjunction. You call conjunction of premises implies conclusion. It will give you a tautology. Then we say that these are all valid, but it is very tedious or it is time taking, lengthy procedure. So it is always better by making use of rules of inference to build arguments or to check whether the given set of arguments or given set of premises are valid or not. And one more example I want to see here. If Joe is a mathematician, then he is ambitious. Observe the statements carefully and how to write them symbolically, and then where to apply your logical rules of inference. If Joe is a mathematician, then he is ambitious. That means if P is, suppose you take the statement P, Joe is a mathematician, Q, Joe is ambitious. So you will get here first statement P implies Q. Again, if Joe is an early riser, then he does not like oatmeal. He does not like oatmeal. So Joe likes oatmeal and you take it as or statement, or you take it as Joe is an early riser, and yes, you take Joe likes oatmeal. So coming to the given premises, if Joe is a mathematician, then he is ambitious, that is P implies Q. If Joe is an early riser, then he does not like oatmeal, that means R implies negation of S. If Joe is ambitious, then he is an early riser, that is Q implies R. Hence, if Joe is a mathematician, then he does not like oatmeal. That is the conclusion he is given. Therefore, what he says, if you convert the given statements in symbolic form, we got them as P implies Q, R implies negation of S, Q implies R. Therefore, you have to check whether P implies negation of S is valid or not. See how you see, you have to form a table like this, assertions and reason. What is the first premise? P implies Q, that is premise 1. Q implies R, premise 3 you take, because from hypothetical law of syllogism or from the law of transitive rule, you have P implies Q, Q implies R will give you P implies R. So, premise 1 and 2, 1 and 3 and transitive rule, you get P implies R, and also premise 2 gave you R implies negation of S. So, premise 2. Now, you have P implies R, R implies negation of S. Again, by transitive rule, you have P implies negation of S. What does it mean? If Joe is a mathematician, then he does not like oatmeal. Is it satisfied or not? Yes, it's got satisfied. So, in this way, you have to check the validity of the statements.
Here, some common fallacies. It is common fallacies means it is sometimes statements are used that is a false conclusions. Yeah. Statements are the, I am taking that is a 2-3 statements. That the statements connectivity I am taking. The resultant may not be get.
Yes.
That is a resultant may not be get means automatically stops, that is a what is the process.
Okay.
So that is called as a common fallacies.
Okay.
Here common fallacies is a clearly, it is a what are the rules we have, okay, that inferences rules is clearly for the applying to the statements, automatically it will be failed.
Okay.
That we can be apply from the proof methods also we can be used. Okay. So here one of that is a false is the inferences rule or other proofs methods that is not a logically valid. There are 3 forms of the
Fallacies.
false inferences we have. That is a example I am taking, negation of it is clearly may yield a false conclusions. Now another is comes to the falsity of the affirming, that is a conclusion, and it is a P tends to Q is the true, then Q is the true, so P is must be the true. Then it is because of false is statement is goes to the true. It is a difficulty. So that it is a such kind of the statements we have hypothetically very difficulty. So that kind of the statements is called as a common fallacies we call.
Okay.
Yeah. Some fallacies are fallacies affirming the consequent, and you have non sequitur fallacies also. So see, suppose here if the price of gold is rising,
Okay.
then inflation surely coming.
Yes.
Inflation is surely coming, therefore price of gold is rising. Can you
Yes.
say, is it true? No, we can't say. This argument is faulty. Why? Because the conclusion can be false even though P implies Q is true,
Okay.
and Q also true. But you have P implies Q meet P is not a tautology.
Yes.
Suppose you are combining those statements and you are checking for their validity using truth tables also, it is not a tautology. So you have conjunction of statements is not a tautology. Conjunction of premises implies conclusion is not a tautology. Then we say that it is a fallacy. Here what is this fallacy? Fallacy in conclusion. Okay. Similarly here opposite of P implies Q is negation of P implies negation of Q. That is also this is also fallacy, is the same as affirming the opposite. The converse Q implies P of P implies Q need not be true, and always converse need not be true. We have seen in many cases. So since the contrapositive of Q implies P is equivalent to P implies Q, we see that affirming the opposite is equivalent to affirming the converse. That means actually in a single word always contrapositive is true, converse need not be true. For many implications P implies Q, then Q implies may true or may not be true. For many problems we have seen that converse need not be true. Suppose next non sequitur fallacy. What is a non sequitur fallacy? Suppose there is incomplete statements are given. Suppose if I say all men are mortal, Socrates is a man, so Socrates is mortal. So what I will do? Socrates is a man, therefore Socrates is mortal if I say, and I missed that statement.
Yes.
So that kind of statements are called fallacies, which comes under non sequitur fallacies.
Yeah, madam.
Yeah.
So how to identify that invalid statements here?
Invalid statements means if at all it is not satisfying any of these four rules: modus ponens,
Okay.
modus tollens, distributive what you call De Morgan's laws, and transitive rule. If they are not satisfying, then we say that they are not valid. Or the other way is, if you form a truth table, conjunction of premises implies conclusion is not a tautology, then given set of statements are not valid. Next, coming to see why here we are taking only one statement P, Q. That means, see, David is playing, he is either playing or doing homework, like that only we are doing. Suppose if we generalize the statements, for that we make use of quantifiers. See, always we say, suppose if you take real numbers and natural numbers, always they say, always there exists a natural number such that natural number is greater than a real number. Like that, always there exists. Why we are calling there exists X? So existential quantifiers. Now we are we want to focus little bit on quantifier. What do you mean by quantifier? That means we are generalizing. So there are two types of quantifiers. One is existential quantifier and universal quantifier. Existential means there exists X. That is the symbol for there exists X. There exists X such that P of X. That means for some X, P of X is true. Or universal means for every X, for every x p of x is true. So, if I say all birds can fly, just even existent using these two quantifiers, we can form the statements, or we can represent the given statements in symbolic form. If I say all birds can fly, all birds, that means if I take x such that b of x means birds, f of x means flying birds. So, if I am saying all birds can fly, for every x b of x implies f of x. Not all birds can fly. Not all birds can fly means there exists x such that b of x and negation of f of x, which you can write it as negation of for every x b of x implies f of x, because we know that p implies q. P implies q is equivalent to negation of p join q. So, this is about quantifiers. And also you have rules of inference for this quantified proposition also. Previously we discussed 4 rules. Now we have fundamental rule 5, universal specification, and fundamental rule 6, universal generalization. So, here if a statement of the form for every x p of x is assumed to be true, then the universal quantifier can be dropped to obtain p of c is true for every x such that for every x p of x implies p of c for all c. Okay. Suppose if I say x and x plus 1, if x plus 1 is the successive of the number x, then see, if that means you know that 1, 2, 3, 4 are natural numbers. Suppose if you take 3, 4, 5, 6 like that. So, all natural numbers you can arrange them. That means if x is a natural number, x plus 1 is also a natural number. That means this is true for all x. Or if I say, if a function 2x plus 1, if I say 2x plus 1 is an odd number, then for every x is natural number, for every x belongs to n, 2x plus 1 is an odd number, then if you take x is 4, then 2 into 4 plus 1, that is also an odd number. Like that you can make universal specification, and at the same time we can say universal generalization also. If I say every integer, every number 4n plus 1 is a prime, means I can generalize. That means if I take some primes 7, 4 into 1 plus 3, suppose if I take that means we can generalize the cases for we can say some primes are of the form 4n plus 1 or 6n minus 1, like that we can do generalization, whereas the specification also we do. These are the 6 fundamental rules. And 7th one is existential specification. If there exists x such that p of x is assumed to be true, then there is an element c such that p of c is true. Similarly, existential generalization. If p of c is true for some element c in the universe, then there exists x such that p of x is true. So, these are the 8 fundamental laws. First one is modus ponens, second one is hypothetical syllogism or transitive rule, third one is De Morgan laws, fourth one is contrapositive or modus tollens, and even fifth one is universal specification, universal generalization, existential specification, existential generalization. So, on the summary, what we have learnt?
Yes. Yeah, thank you madam, and thank you sir, thank you for coming here. Students, so this is a fundamental logical brief and it is a very nice explanation. So, mathematical topics when we can understood means if we have the good teacher with good explanation, then only we can understood, and that sir and madam is explained very well. I think it's very useful for you, and thank you so much.
Any questions?
Any questions?